This is the sixth and last module of this chapter. In previous modules, from module 1 to 4, we have described several methods to find the solution of a system of linear equations. In these methods, we have assumed that the system is consistent, that means it has a solution, and the system is well posed. But in many applications, we have seen that the system of equations may be inconsistent or may be not well posed, that means ill posed. In this module, we shall describe a method to solve the inconsistent system of equations, and we also describe two methods to solve ill conditioned system of equations. First of all, we define the norm of a vector. Let x be a vector of dimension m, that means it contains n number of elements. The norm of a vector is the size or length of x and it is denoted by double bar x. We know the norm is a mapping from the set of vectors to a set of real numbers. That means the norm satisfies the following three conditions. This is well known conditions for a norm. The first one is called the non-negativity condition, second one is called the homogeneous condition, and third one is called the triangle inequality. And different types of norms are defined for different application. The first one is called the column norm, that one is denoted by norm 1. Second one is called the Euclidean norm, this is very useful and widely applied norms, that one denoted by norm 2. And norm 3 is the maximum norm or called the uniform norm. These are the vector norms. Similarly, we can define the matrix norm. Let A and B be two matrices such that A plus B and A into B are defined. The matrix norm is also defined by double bar A, and that one is satisfied by the following conditions. The first condition is non-negativity condition. That means norm of a matrix should be greater than or equal to 0, and if the matrix is null matrix, then norm is 0. The second one is the homogeneity condition, where alpha is a scalar number. Third condition is the triangle inequality. That means the norm of A plus B less than or equal to norm of A plus norm of B. Fourth condition is norm of A into B less than equal to norm of A into norm of B. And it is obvious that for any positive integer k, from equation 10 we can write norm of A to the power k less than or equal to norm of A power k. Like vector norms, we can define different kind of matrix norm. The first norm is denoted by norm 1, this is the column norm. Second one is the Euclidean norm, which is the square root of the sum of square of all elements. And third norm is the infinity norm, and this is called the row norm of a matrix. The Euclidean norm is also known as Arnhart-Schmidt norm and Schur norm or the Frobenius norm. Now we consider a very interesting system of equations. The first equation is x plus 1/3 y equal to 1.33. Second equation is 3x plus y equal to 4. It is easy to verify that this system of equation has no solution. That means it is a inconsistent system of equation, but for different approximate values of 1/3, one can get different interesting solution of the system of equation 15. First we consider 1/3 is approximately equal to 0.3, then the system becomes x plus 0.3 y equal to 1.33, and second equation remains unchanged, that one 3x plus y equal to 4. And solution of this system of equation is x equal to 1.3, y equal to 0.1. But if we approximate 1/3 as 0.33, then first equation is reduces to x plus 0.33y equal to 1.33, and second equation remains unchanged, that one 3x plus y equal to 4. and solution of this system of equation is x equal to 1, y equal to 1. And in second case, if we approximate 1/3 as 0.333, then first equation is changed to x plus 0.333y equal to 1.33. Second equation unchanged, and solution of this system of equation is x equal to -2, y equal to 10. And if we consider 1/3 equal to 0.333343, then first equation reduces to x plus 0.3333y equal to 1.33, and the solution of this system of equation is x equal to 100, y equal to -32. So it is very interesting that minor change of the coefficient of y in first equation, the solution is drastically changed. That means if we compare the first row and third row of this table, then we see that the coefficient of the third system of equation is increased by 0.0033, but the solution is 100 times more than the solution obtained in first system of equations of this table. And similarly, the solution obtained for third system of equation is y equal to -32, whereas the y equal to 1 for first system of equation. Note that the above system of equations and their solutions, these are very confusion situations, but the question is, what is the best approximation of 1/3? Is it 0.3 or 0.3333? Observe that the solutions are significantly increased when the coefficient of y in first equation is slightly increased. That is, a small change in the coefficient of y in first equation of the system produces large change in the solution. This type of system of equations are called ill-conditioned or ill-posed system or system of equations. On the other hand, if the change in the solution is small, for small changes in the coefficient, then the system is called well-conditioned or well-posed system of equations. The condition number is a parameter to identify whether a given system of equations or the corresponding matrix is well-conditioned or ill-conditioned. In general, when determinant of the coefficient matrix is small, then the matrix A is ill-conditioned. Many parameters are suggested or defined to measure the ill-condition of a matrix. One of the simple methods is defined below. Let A be a matrix and the condition number, that one denoted by cond A, is defined by cond A equal to norm of the matrix A into norm of the matrix A inverse. If cond A is large, then the matrix is called ill-conditioned and the corresponding system of equations is called the ill-conditioned system of equations. If it is small, then the matrix is called the well-conditioned matrix and the corresponding system of equations is called well-conditioned system of equations. The value of cond A lies between 0 and infinity. It is large, then we say that the matrix is ill-conditioned, but there is no definite meaning of a large number, so this measure is not suitable to identify whether a matrix is ill-conditioned or not. Now we define another parameter whose value lies between 0 and 1. Let A be a matrix and we define a parameter Ri, which is equal to root over sum of the square of the elements of the ith row, and then we define the quantity nu A, which is equal to determinant of the matrix A divided by R1 into R2 dot dot Rn. This measures the smallness of the determinant of the matrix A. It can be shown that the value of nu lies between -1 and 1 because the determinant value may be negative or positive. If the absolute value of nu A is close to 0, then the matrix is ill conditioned, and if it is close to 1, then the matrix is called well conditioned. Let us consider a matrix A whose first row is 1, 4, second row is 0.22, 1. And for this matrix, R1 equal to root over 17, R2 equal to 1.0239, and determinant of this matrix is 0.12, and hence nu A equal to 0.0284. And for the matrix B, R1 equal to root over 34, R2 equal to root over 8, and determinant of B is 16. Therefore, nu of the matrix B equal to 0.9702. Thus, the matrix A is ill conditioned because the nu of this matrix, that means nu A is very small, close to 0, while the matrix B is well conditioned as its value is close to 1. The least square method can be used to solve a system of inconsistent set of equations. Let such system be Ax equal to B, where A is a matrix of order m by n, x and b are the vectors of order n by 1 and m by 1 respectively. Note that the coefficient matrix is regular, so it can determine the more Penrose inverse of this matrix. Now, a solution x dash is said to be least square if Ax dash minus b is not equal to null vector, but the norm of this vector is minimum. The solution xm is called the minimum norm least square solution if norm of the vector xm is less than or equal to norm of any vector x1 for any vector x1 such that norm of the vector x1 minus b less than or equal to norm of the matrix column matrix x minus b, and this condition is true for all x. Since the matrix A is rectangular, so its solution can be determined by the formula x equal to A plus B, where A plus is the more Penrose inverse of the matrix A. Since the more Penrose inverse is unique, therefore the minimum norm least squares solution is unique. If x is an exact solution of the system of equations Ax equal to b, then Ax minus b is a null vector, it is obvious. Otherwise, Ax minus b a non-null matrix of order m by 1. In explicit form, this vector is this one. The first element is a11 into x1 plus a12 into x2 plus a13 plus a1n xn minus b1, and similarly the other elements. Let square of the norms of the vector x minus b be denoted by s. Therefore, s is given by this formula, s equal to summation I equal to 1 to m summation over j equal to 1 to n aij minus x minus bi whole square. The quantity s is called the sum of square of residual. Our aim is to find the vector x such that the sum of square of residual s is minimum. The sufficient conditions for which s to be minimum are del s del x1 equal to 0, del s del x2 equal to 0, del s del xn equal to 0. Note that the system of equations 22 is non-homogeneous and contains n equations with n unknowns x1 to xn. This system of equations can be solved by any method described in previous modules. Now we consider an example to illustrate the inconsistent system of equations. Now let A be a matrix of order 2 by 2 whose first row is 4 8 and second row is 1 2. We have to determine the G inverse of this singular matrix A and hence find a least square solution of the inconsistent system of equations 4x plus 8y equal to 2 and x plus 2y equal to 1. For this singular matrix, the Moore Penrose inverse is obtained as A plus equal to a 2 by 2 matrix whose first row is 4 by 85, 1 by 85, second row is 8 by 85, 2 by 85. In this system of equation Ax equal to B, the coefficient matrix A equal to 4, 8, 1, 2 and the unknown vector x equal to xy and right hand vector b equal to 2, 1. And the solution of this system of equation, obviously this solution is least square solution which is equal to x equal to a plus b, that is x equal to 1 by 85, 4, 1, 8, 2 into the column vector 2, 1. After simplification it becomes a column vector whose first element is 9 by 85, second element is 18 by 85. Therefore, the solution of the given system of equation is x equal to 9 by 85, y equal to 18 by 85. This is called the least square solution because the given system of equation is inconsistent. Now we consider another system of equations, and this system of equations contains 4 equations and 2 variables, and also we have to determine the sum of square of residuals. Let x star and y star be the least square solution of the given system of equations. Then the sum of square of residuals s is given by this formula, that means square of x star plus 2y star minus 2 plus x star minus y star minus 1 whole square plus x star plus 3y star minus 2.3 whole square plus 2x star plus y star minus 2.9 whole square. Now the problem is to find the values of x star and y star such that s is minimum. So for this case the normal equations are del s del x star equal to 0 and del s del y star equal to 0. After simplifications the normal equations are this one, that means 2 into x star plus 2y star minus 2 plus 2 into x star minus y star minus 1 plus 2 into x star plus 3y star minus 2.3 plus 4 into 2 x star plus y star minus 2.9 equal to 0, and second equation is obtained from the second equation del s del y star equal to 0. After simplification these two equations reduce to 7x star plus 6y star equal to 11.1 and 6x star plus 15y star equal to 12.8. The solution of these equations is x star equal to 1.3 and y star equal to 1/3, that one is taken as 0.3333, correct up to 4 decimal places. So this is the least square solution of the given system of equations. Now the sum of square of residual is s equal to 1.3, this is the value of x star plus 2 into 0.3333 minus 2 whole square and so on. After simplification it becomes 0.0033, that means sum of square of residual is 0.0033, which is very close to 0. That means x star equal to 1.3 and y star equal to 1/3 is a good solution of the given system of linear equations. We have described least square method to solve an inconsistent system of linear equations. Now we consider yield condition system of equations. Two useful methods or two widely used methods. One is called relaxation method and other is called successive over relaxation methods are described to solve ill conditioned system of equations. The relaxation method is based on Gauss-Jordan iteration method and successive over relaxation method is based on Gauss-Seidel iteration method. Let us consider the following ill conditioned system of equations. Summation over j equal to 1 to n aij xj equal to bi. This is the ith equation where I equal to 1 to n. Let x1 tilde, x2 tilde, xn tilde be an approximate solution of the above system of equations. Since this is an approximate solution, therefore summation aij xj tilde is not necessarily equal to b. For this solution, let the right hand vector be denoted by bi equal to bi tilde. Therefore, the equation 23 becomes summation aij xj tilde equal to bi tilde where I equal to 1 to n. Subtracting equation 24 from equation 23, we get summation over j equal to 1 to n aij into xj minus xj tilde equal to bi minus bi tilde. Note that xj minus xj tilde is the difference between the exact solution and the approximate solution, and similarly bi minus bi tilde represents the difference between right hand vectors. That is, this equation can be written as summation over j equal to 1 to n aij epsilon I equal to di, where epsilon I equal to xi minus xi tilde, that one represents the error, di is the difference between the right hand vectors bi and bi tilde, and this is true for all I equal to 1 to n. Now equation 25 is again a system of linear equations whose unknown are epsilon 1, epsilon 2 up to epsilon n. By solving this system of equations, we obtain the values of epsilon 1 to epsilon n, and hence the new solution is given by xi equal to epsilon I plus xi tilde. Xi tilde is the approximate solution and epsilon I is the solution obtained from the system of equation 25. Therefore, xi equal to epsilon I plus xi tilde is the better approximate solution of the variable xi. This technique may be repeated to get more better solution of the given system of equations. Now we describe the relaxation method to solve an ill conditioned system of equations. Let j equal to 1 to n over summation aij xj equal to bi. This is the ith equation of the given system of linear equations, and let xk, the vector xk, which is equal to x1k, x2k up to xnk transpose, be the kth iterated solution of the above system of linear equations. Then we get summation over j equal to 1 to n aij xjk, which is approximately equal to bi for all I equal to 1 to n. Now we denote the kth iterated residual for the ith equation by Rik. Therefore, the value of Rik is defined by Rik equal to bi minus summation over j equal to 1 to n aij xjk, where I equal to 1 to n. That means that this is the difference between right hand side and left hand side of an equation. If Rik equal to 0 for all I equal to 1 to n, that means if the residuals are 0 for all equations, then x1k, x2k up to xnk transpose is the exact solution of the given system of equations. If the residuals are not 0 or not very small for all equations, then we apply the same procedure to reduce the residuals. In relaxation method, the solution can be improved successively by reducing the largest residual to 0 at that iteration. To to get the first convergence, the equations are rearranged in such a way that the largest coefficients in the equations appear in the diagonals. That means the reduced system of equations is diagonally dominant. The aim of the relaxation method is to reduce the largest residual to 0. Now we assume that Rp with the largest residual in magnitude occurs at the pth equation for a particular iteration. Then the value of the variable xk be increased by dxp, where dxp is defined by minus Rp by app. Rp is the residual for the pth variable or pth equation. That is, xp is replaced by xp plus dxp to relax xp, that is to reduce Rp to 0. Then the modified solution after this iteration is xk plus 1, that means the solution obtained at the k plus 1 iteration, which is equal to x1k, x2k dot xp minus 1k, and the pth values is xp plus dxp, then xp plus 1k up to xnk. So this is the kth plus 1 iterated value of the given system of equations. The method is repeated until all the residuals become 0 or tends to 0. So this is the termination condition. Now we describe another method, another modified method of relaxation method called successive over relaxation method. In this method, a suitable relaxation factor W is introduced. The ith equation of the system of equations, summation over j equal to 1 to n, aij xj equal to bi for all I equal to 1 to n. The ith equation is j equal to 1 to n, aij xj equal to bi. Now we decompose this equation into two parts. The first part is summation over j equal to 1 to I minus 1, aij xj plus summation over j equal to I to n, aij xj equal to bi. That means the first term contains I minus 1 terms and second term contains remaining terms. Let x10, x20 up to xn0 be the initial solution of the given system of equations, and x1k plus 1, x2k plus 2 up to xi minus 1k plus 1, xik, xi plus 1k up to xnk be the solution when ith equation is being considered. Then the previous equation, that means equation number 29, becomes summation over j equal to 1 to I minus 1, aij xjk plus 1. That means when we consider the ith equation, the value of the first I minus 1 variables, that means x1 to xi minus 1 are available. So in first term we have replaced xj by xjk plus 1 plus summation over j equal to I to n, aij xjk equal to bi. Since x1 k plus 1, x2 k plus 1 dot xi minus 1 k plus 1 comma xi k comma xi plus 1 k up to xn k is an approximate solution of the given system of equations. Therefore, the equation 30 becomes this form. The residual at the ith equation is Ri equal to Bi minus summation over j equal to 1 to I minus 1, aij xj k plus 1 minus summation over j equal to I to n, aij xj k. This is true for all I equal to 1 to n. So this is the residual for ith equation. Now we denote the differences of xi's at two consecutive iterations by epsilon I k, and it is defined as epsilon I k equal to xi at k plus 1 iteration minus xi k. That means the difference between the values of xi at two consecutive iterations k plus 1 and k. In successive over relaxation method, it is assumed that aii epsilon I k equal to w ri, where W is the relaxation factor, Ri is the residual defined by equation 31, and epsilon I k is the error occurred at the ith variable at kth iteration, and W is called the relaxation factor. Thus, equation 32 becomes aii xi k plus 1 equal to aii xi k minus W into the right hand part of the above expression, that means equation number 32. And this relation is valid for all I equal to 1 to n and k equal to 0, 1, 2 up to infinity. The iteration process is repeated until desired accuracy is achieved. The above iteration method is called over relaxation method when W lies between 1 and 2, and this method is called under relaxation method when W lies between 0 and 1. When W equal to 1, the iteration method becomes the well known Gauss-Seidel iteration method. Now we consider a system of equations. Obviously it is an ill conditioned system of equations to solve by successive over relaxation method by taking relaxation factor W equal to 1.02. The SOR scheme, that means successive over relaxation scheme, is given by 4x1k plus 1 equal to 4x1k minus 1.02, that one is the relaxation factor, into 4x1k plus 2x2k plus x3k minus 5. This is obtained from first equation, and from second equation we obtain the second iteration scheme or second equation, and from third equation we obtain the last equation. Let x10, x20, x30 equal to 0 be the initial solution of the iteration scheme, and all other calculations are shown in the following table. Note that the row number 8 and 9 are same. That means we terminate the repetition process at 9th iteration, and the solution of the given system of equation is x1 equal to 0.7083, x2 equal to 0.9583 and x3 equal to 0.25, correct up to 4 decimal places. In this chapter, we have described several methods to solve a system of linear equations, including inconsistent system of equations and ill-conditioned system of equations. Also, we have introduced different methods to find the inverse of a matrix. That matrix may be a singular matrix, may be non-singular matrix, or may be a rectangular matrix. For the rectangular matrix and singular matrix, the generalized inverse is described in module 5. The system of inconsistent equations are solved by least square method. That one is described in module 6. Also, we have described two important methods to solve an unconditioned system of equations, and first method is known as relaxation method and second method is known as successive over relaxation method. And all these methods are illustrated by considering different interesting examples.